Okay, class, in this lesson, we are going to learn to use triangle bisectors to solve problems. So let's go ahead and get started. So the first theorem is called the concurrency of perpendicular bisectors. And what this means is that the perpendicular bisectors of the sides of a triangle, so all three sides perpendicular bisectors, are considered concurrent, or they intersect at a point that is equidistant from the vertices. Okay, so let me go ahead and draw what we just said so that you have a better perspective of what this means. So we're going to take side AB and we're going to bisect it perpendicularly. Okay, so the midpoint is going to be right about here, and we're going to draw a perpendicular line. Okay, and then we're going to do the same thing for a second side, and it doesn't matter which side of the triangle. So we're going to go ahead and pick side BC, and we're going to do the same thing. We're going to draw a perpendicular bisector. Okay, and where it intersects at this point right here, okay, that is what's considered concurrent at a point, meaning all of these perpendiculars, bisectors, so we've drawn two. We could draw a third one relative to AC, but that's not necessary. We just need to draw two of them, but where they intersect is the concurrency of the point. Okay, and what this theorem is basically saying is that from this intersection to each of the vertex of this triangle are the same distance. So let me go ahead and just draw that out in blue. So this distance here, and this distance here, and this distance here, they're all the same. So let me go ahead and label this point intersection as P, and I'm going to just make this dotted so that we differentiate from the side of the triangle, I mean. And let's go ahead and do this one. All right, so what we're saying here then is that segment or distance AP is equal to BP, and that is also equal to CP. Okay? All right, so let's go ahead and take a look at this first example. Okay? So in this example, we're told that the bisectors of all three sides of triangle ABC intersect at point P. And the question is, if segment AP is equal to 8, what is the length of segment BP? And then what is the length of segment CP? Okay, so if we were to draw the bisectors of all three sides, they would look like this. We're bisecting, which means this is perpendicular or 90 degrees, and the distance are the same on that side. And we're going to do the same thing with side BC. This is also 90 degrees. Okay, and it bisects that side. So those two segments are the same. And we'll go ahead and do the third one. Okay, so this is perpendicular. And that means this side here is bisected. So both of those sides are equal. And we are told that they intersect at point P. So let's go ahead and label that as point P. Okay. All right, so now the question is, if AP, which is right here, if AP is 8, then what is the length of BP? Okay, so based on the theorem that we just learned, concurrency of perpendicular bisectors, okay, we know that AP is equal to BP, which is also equal to CP. Okay, so if AP is 8, then BP, segment BP, is 8, and segment CP is also equal to 8. Okay, so let's go ahead and finish drawing segment CP so that you can visually see that those lengths are equal. Okay, now there's also something to note about this particular theorem. So let's go ahead and go to this next section here. And it has to do with what's called a circumscribed circle. Okay, so a circle that contains all 3 vertices, so each of these vertex of this triangle. So the circle contains all 3 vertices of a triangle. That is considered a circumscribed circle of the triangle. Okay, and then by the concurrency of perpendicular bisector theorem, which is a theorem that we just learned, the perpendicular bisectors, okay, so that's right here, perpendicular bisectors, intersect at a point that's equidistant from the vertices. Okay, so if we drew the perpendicular bisectors of this side, perpendicular bisector of this side, and the perpendicular bisector of that side, okay, this point to each of the vertex would be the same distance, which is essentially what we learned about the theorem. Okay, and the point of concurrency of the perpendicular bisectors of a triangle, so basically the middle of this circle, is also called the circumcenter. So the circumcenter is the center of the circumscribed circle of the triangle. Okay, so the point of all of this is that when we find this point, which is established by the perpendicular bisectors of each of these sides, okay, we find that this point to each of the vertex are the same, and it also happens to be the center of the circumscribed circle. Okay? All right, so let's go ahead and move on to the next example. So this is a potential real scenario where a city manager wants to place a new emergency siren so that it is the same distance from the school, hospital, and the recreation center. Okay, so the question is, where should the emergency siren be placed? Well, first thing to do is to connect all 3 of these with straight lines. And when we do, we have established a triangle. Okay, and then the next thing we're going to do is draw a perpendicular bisector for, we'll say 2 of the sides for now. We don't need to do all 3. Okay, so that's 1. This is perpendicular, and it cuts this exactly in half. And we're going to go ahead and draw a perpendicular bisector right here. So that's about perpendicular, and both of those segments are the same distance. So this intersection is our circumcenter. Okay, and what this tells us is that the distance from this intersection to each of the vertex of the triangle are the same distance, and the vertex of each of these triangles happen to be the location of these 3 buildings, right? The hospital, so from here to here, that distance is the same from here to the recreation center, and then this intersection to the school, that distance is also the same. So then the answer is the siren should be placed at this point of intersection, which is the circumcenter. Okay, and we established that by drawing two perpendicular bisectors, one of this side of the triangle and then the other of this side of the triangle. Okay, all right, so let's go ahead and move on to the next theorem. Okay, and this next theorem is very similar to the previous theorem with a slight variation. So this is called the concurrency of angle bisectors. And what this basically is saying is that the angle bisectors, okay, of the angles of a triangle are concurrent at a point that it is equidistant from the sides of the triangle. Okay, so what is this saying? Basically what this is saying is if we draw a angle bisector, okay, so this angle is the same as that angle, and then we draw another angle bisector, and this angle is the same as that angle, and we can go ahead and draw the third one, although it's not necessary. We draw this angle bisector. We know that this angle is also the same as that angle. Okay, so all three are angle bisectors. Okay, and they create an intersection. So that point to that distance from that point to the side of the triangle, so in other words from here to here, this is the shortest distance, which happens to be a right angle. That distance is also the same as the distance from the intersection to that distance, and it also happens to be the same distance from the intersection to this side of the triangle. Okay, all right, so let's go ahead and take a look at a particular example. So what's interesting is in the previous theorem we had a circumscribed circle. In this case we have an inscribed circle. So the circle that intersects the side of the triangle at exactly one point. So this is one intersection, this is another intersection, and this is another intersection. Okay, so the circle is intersecting the triangle at exactly one point and has no point outside of the triangle. Okay, so the circle does not go outside of the triangle. That is considered an inscribed circle of the triangle. Okay, and so by the concurrency of angle bisectors theorem, the angle bisectors of a triangle, so the angle bisector, right, what we just drew earlier, bisects this angle here, bisects this angle here, and bisects this angle here. They intersect at a particular point, and that point happens to be the same distance to each side of this triangle as drawn here. Okay, and that point of concurrency, or in other words where they intersect, that is called the incenter. Okay, so the incenter also happens to be the center of the inscribed circle. Okay, all right, so let's go ahead and move on to example 5 and let's work this out. So in example 5 we are told that QP, so this distance QP, is 3 times the quantity x plus 1, and the distance RP is equal to 5x minus 3. And the question is, what is the radius of the inscribed circle of JKL? Okay, so here's triangle JKL. Okay, and so we basically would know that there is an inscribed circle. Okay, an inscribed circle would fit in here. Okay, so let me attempt to go ahead and draw that. I'm going to do this in green. Here's the inscribed circle. Okay. And so the question is, what is the radius of the inscribed circle? Okay. So based on the theorem that we just learned, okay, we know that this in-center is the center of the inscribed circle. Okay, so this happens to be the center of this circle, and this distance here is the radius. Okay, and we know that this distance is equal to this distance as well. So in other words, segment QP is equal to RP. Okay, well, we're told that QP is 3 times the quantity x plus 1, and we're going to set that equal to RP, which is 5x minus 3. So we can go ahead and solve for x first, and that's going to become 3x plus 3. Okay, we're going to use the distributive property, so we're going to multiply these first, and then multiply those next, and that's going to equal 5x minus 3. Okay, and then to further solve for x, we need to move this 3x to the other side of the equation, and we do that by subtracting 3x from both sides. And when we do, these cancel out, and we're left with 3 is equal to 2x minus 3. And then what we want to do is move this negative 3 to the other side of the equation. And to do that, we have to add 3 to both sides. And when we do, we get 6 is equal to 2x. These cancel out. Okay, and then the last step here is to isolate x. And to do that, we need to divide 2 on both sides. Okay, and when we do, we get 6 divided by 2 is equal to 3. And so 3 is equal to x because those 2's cancel out. Okay, so now that we know what the value of x is, we still have to answer the question, what is the radius of the inscribed circle of triangle JKL? Well, we know that the radius is PR or RP, or it could be QP. Either one of these is fine. So let's go ahead and use the values of RP. So we know RP is equal to 5x minus 3. We just solved for x. So we're going to insert x in here. And so RP is going to equal to 5 times the value of x, which is 3, minus 3. And this works out to 15 minus 3. Or the radius is 12. Okay? Hopefully that made sense. If any of this was confusing or if you need further clarification, please go back to the beginning of the recording and listen to it again. Thank you.